Welcome back. I am Muammar Lone, and in our previous episodes, we've explored the foundations of NLP, linguistic concepts, and text processing. Today, we're going to tackle one of the most fascinating challenges in NLP. How do we transform text into numbers that machines can understand? Think about it. Computers don't naturally understand words and sentences like we do. They work with numbers. So how do we bridge this gap? How do we take something as rich and nuanced as human language and convert it into mathematical representations without losing its meaning? Imagine trying to explain the difference between good and great using only numbers, or capturing the similarity between king and queen. Today, we'll explore the ingenious techniques that make this possible. The challenge of representation. Let's start with a fundamental question. What makes a good text representation? Consider these sentences. The cat sat on the mat. A kitten rested on the rug. Dogs sleep in their beds. To a human, the first two sentences are more similar in meaning than the third. But how do we capture this numerically? We need representations that preserve semantic meaning, capture word relationships, handle vocabulary variations, scale efficiently, enable meaningful comparisons. This is where feature engineering comes in, the art and science of transforming text into numerical features that machines can process. Bag of words, the foundation. Our journey begins with one of the simplest yet most powerful techniques, the bag of words BOW model. Think of it like this. Imagine you have a bag full of words, and you're just counting how many times each word appears, ignoring their order. Let's try an example. Sentence. The cat sat on the mat. Becomes the two cat one, sat one, on one, mat one. This creates a vocabulary where each unique word gets a position, and we can represent any text as a vector of numbers. For instance, vocabulary: the cat sat on mat, dog ran. Sentence vector: 2 1 1 1 1 0 0. But this basic approach has limitations, loses word order, ignores relationships, treats all words equally, creates sparse vectors, misses context. Let's see how we can address these challenges. Term. Frequency inverse document frequency, TF-IDF. Now we're moving to a more sophisticated approach, TF-DF. This technique answers a crucial question. How do we identify which words are truly important in a document? Think about news articles. Words like the and in appear frequently but carry little meaning. Meanwhile, words like cryptocurrency, pandemic, or election might appear less often but are crucial for understanding the content. Let's break down TF-IDF. Term frequency, TF. How often a word appears in a document, normalized by document length, captures local importance. Inverse document frequency, IDF. How rare a word is across all documents. Penalizes common words, rewards distinctive terms. For example, let's analyze these headlines. 1. New vaccine shows promising results. 2. New restaurant opens in downtown. 3. New technology revolutionizes industry. The word new appears in all three, so it gets a low IDF score. But vaccine, restaurant, and technology appear only once, getting higher IDF scores. This creates more meaningful representations where important words have higher weights. Common words are downplayed. Document length is normalized. Unique terms are emphasized. Context is better preserved. N-grams, capturing sequences. While BO and TF-IDF handle individual words well, they miss important phrases and word combinations. This is where n-grams come in. Instead of looking at single words, n-grams capture sequences, unigrams, single words, the cat sat, bigrams, pairs, the cat and cat sat sat on, trigrams, triplets, the cat sat on. Let's analyze this sentence. The black cat sat on the mat, unigrams, the her 2, black 1, cat 1, sat 1 on 1, mat 1, bigrams, the black 1, black cat 1, cat sat 1, sat on 1, on the 1, the mat 1, trigrams, the black cat 1, black cat sat 1, cat sat on 1, sat on the 1, on the mat 1. This captures word order, common phrases, local context, structural patterns, linguistic units, but it also introduces challenges, vocabulary explosion, data sparsity, computational complexity, memory requirements, rare sequence handling, word embeddings, dense representations. Now we enter the realm of word embeddings, one of the most powerful innovations in NLP. Instead of sparse vectors, we represent words as dense vectors in a continuous space. Imagine a multi-dimensional space where similar words are close together, relationships are preserved, analogies can be computed, meaning is distributed, context is captured. For example, in this space, king, man, plus woman, queen. Paris, France, so Italy roams quick is closer to fast than to slow. Let's explore some popular embedding models. Word. Vec learns from context, produces dense vectors, captures semantic relationships, enables word analogies, supports composition, global vectors, uses global statistics, balances local and global context, provides efficient training, creates meaningful spaces, handles rare words, fast text, works with subwords, handles unknown words, supports morphology, enables composition, improves rare word handling. Advanced feature engineering. Beyond these fundamental techniques, let's explore some advanced approaches. Document embeddings, paragraph vectors, Doc2-Vec models, sentence transformers, hierarchical representations, cross-document relationships, positional features, word position encoding, structural markers, section identification, discourse signals, sequential patterns, linguistic features, part-of-speech tags, dependency relations, named entities, semantic roles, syntactic structures, custom features, domain-specific patterns, expert knowledge, business rules, user behavior, temporal aspects, real-world applications. Let's see how these techniques enable practical applications. Search engines, query understanding, document matching, relevance ranking, query expansion, result clustering recommendation systems, content similarity, user preferences, item relationships, contextual recommendations, trend analysis, classification, topic categorization, sentiment analysis, language identification, intent recognition, spam detection, information extraction, named entity recognition, relationship extraction, event detection, fact verification, knowledge, graph construction, thus, optimization, and best practices. Success in feature engineering requires careful consideration of pre-processing decisions, tokenization choices, normalization level, vocabulary size, n-gram range, stop word handling, model selection, task requirements, data characteristics, performance needs, resource constraints, maintenance considerations, quality, assurance, feature validation, coverage analysis, error detection, performance monitoring, regular updates, scalability, processing efficiency, memory management, batch processing, incremental updates, distributed computing, future trends. The field of text representation is rapidly evolving. Contextual embeddings, BERT-like models, dynamic representations, transfer learning, fine-tuning approaches, task-specific adaptations, multimodal features, text-image combinations, audio-text alignment, video understanding, cross-modal learning, unified representations, privacy, preserving representations, differential privacy, federated learning, secure computations, anonymous features, ethical considerations, efficient representations, model compression, quantization, knowledge distillation, sparse operations, hardware optimization. As closing, as we conclude our exploration of text feature engineering, remember, representation matters. Context is crucial. Balance complexity and utility. Consider your use case. Test thoroughly. In our next episode, we'll dive into advanced word representations and neural network approaches. Until then, try this exercise. 1. Take a set of similar documents. 2. Apply different feature engineering techniques. 3. Compare the results. 4. Analyze the trade-offs. 5. Consider the applications alone. And thank you for joining me in this journey through the art and science of text representation. Remember, every word can be a number, and every number can tell a story. Keep exploring, keep engineering, and I'll see you next time. Stay curious and keep vectorizing.